Okay, dear students, we shall continue the properties of eigenvalues and eigenvectors. In the previous two video lectures, we have seen some of the important properties of eigenvalues and eigenvectors. So, in this video, we shall see some more properties of eigenvalues and eigenvectors. Before going to the properties, you look at this table. So in the first row we are having the matrix A here, minus 4, minus 6, 3, 5. If you calculate the eigen values for this by finding the CH equation or CH polynomial, you are going to get the eigen values as 2 and minus 1. All of you should find out the eigen values for this matrix. In the second row, what I do is I multiply the matrix A by 3. How you multiply the entire matrix A? By a scalar number. By multiplying that scalar to each and every element inside the matrix. Multiply minus 4 by 3, we get minus 12. Multiply minus 6 by 3, we get minus 18, and so on. This is your matrix 3A. Now you calculate what are the eigenvalues of 3A. The matrix 3A, you find out the eigenvalues for this. You know how to calculate eigenvalues for this. It is determinant of minus 12 minus lambda minus 18, 9, minus 15 minus lambda is equal to 0. Evaluate the determinant, you get CH equation. You solve that quadratic equation, you will get two values, and those two values are 6 and minus 3. You should solve that CH equation. You get like this, 6 and minus 3. And next what I do is I multiply the matrix A by scalar number 5. So you will get minus 20, minus 30, 15 and 25. Next step, I am going to calculate eigen values for the matrix 5A. Minus 20 minus lambda, minus 30, 15, 25 minus lambda, determinant is equal to 0. You evaluate that, you are going to get a quadratic equation in lambda. Solve that, you are going to get the values of lambda as 10 and minus 5. Okay. Next, multiply the matrix A by minus 2. You will get the matrix like this. Minus 2 into minus 4 is plus 8. Minus 2 into minus 6 is plus 12. And then minus 6, minus 10. Next, you calculate eigenvalue for this matrix. You know the eigenvalues for this matrix is minus 4 and minus 4 and 2. The eigenvalues for this matrix are minus 4 and 2 we get. Now my question is, compare the eigenvalues of A and 3A. You see, eigenvalues of A, 2 minus 1, 3A, 6 minus 3. Compare the eigenvalues of A and 5A. Eigenvalues of A, 2, here we have 10, minus 3, here we have minus 5. Eigenvalues of A and minus 2A. See, eigenvalue of A is 2, eigenvalue of minus 2A is minus 4. Eigenvalue of A is minus 1, eigenvalue of minus 2A is 2. So now my question is, can you find any relation between eigenvalue of A and 3A? 2, 6, minus 1, minus 3. Yeah, you are right. See, I have multiplied A by 3, then eigen values are also multiplied by 3. Am I right now? Similarly, if I multiply matrix A by 5, you see eigen values are also multiplied by 5. 5 into 2 is 10. 5 into minus 1 is minus 5. Observe the last row. If I multiply A by minus 2, then eigenvalues are also multiplied by minus 2. You see, eigenvalues of A are 2 minus 1. Multiply these values by minus 2. You will get minus 4 and 2. These are the eigenvalues of the matrix minus 2A. So therefore, what we can conclude from this table is, if lambda is an eigenvalue of the matrix A, If I multiply the matrix A by some number, say k, then we get k into A matrix. The eigenvalues of that k into A matrix are k into lambda. Am I right now? If I multiply the matrix A by a scalar k, then eigenvalues are also multiplied by the same scalar k. If lambda is an eigenvalue of A, then k lambda is an eigenvalue of matrix k into A. This is what is the important property of eigenvalues. Let us try to prove the property in the next slide. The property is like this. If lambda is an eigenvalue of A matrix, then k lambda is an eigenvalue of k into A, where k is a non-zero number. K is non-zero number. Let us try to prove this one. You take A be a square matrix and x be the eigenvector corresponding to the eigenvalue lambda. Matrix A, x is eigenvector, lambda is the eigenvalue. So whenever you come across with x, the eigenvector, you should remember that equation. What is that equation? Yes, you are right. Ax is equal to lambda x. Then we have, this is the very important equation you should remember. Ax is equal to lambda x. What I will do in the next step is, I pre-multiply both the sides by the scalar number k. Multiply k both the sides. You will get like this. In the next step, I combine k and a. Put them in the box. Similarly, I combine k and lambda, put them in the box like this. Okay, you can do like that. Interchange the bracket and make a group of k into a. Here also interchange the bracket, make the group of k into lambda, where k is number. Remember, k is not matrix. K is not matrix, k is a number, just like 2, 3, minus 2, like that. Okay, yeah, k into a, x is equal to k lambda into x. So now observe the first equation and the last equation. You see, if we have ax is equal to lambda x, then you say x is the eigenvector corresponding to eigenvalue lambda. I mean, for the matrix A, x is the eigenvalue. So compare the last equation, kax is equal to k lambda into x, with the given, the first one. In place of a, we have k into a. In place of x, we have here also x. In place of lambda, here we are having k lambda. In place of x, we are x. In place of lambda, we are having k lambda. Which means that for the matrix k into a, k lambda is the eigenvector. That's all the proof. You see, in ax is equal to lambda x, we say lambda is the eigenvalue of matrix A. This last equation is same as that of this first one. What is the change? The change is, only thing is that in place of a, we are having ka. In place of lambda, here we are having k lambda. Therefore, what we can conclude is k lambda is the eigenvalue of the matrix Ka. That's all the proof. Very simple proof. Now let us move on to the next property. Before going to the next property, you observe this table. I am repeating, don't write this table in your notes. This is just for your sake only. So now, in the first row we have the matrix A. I am taking the same example whose eigenvalues are 2, minus 1. What I do is, next I am computing A square, A into A. You know how to multiply two matrices, A into A. Write down A 2 times and multiply. Row into column. You know the method of multiplying two matrices. If I calculate A square, the matrix will be like this: minus 2, minus 6, 3, 7. You calculate at your home. You are going to get A square. Then you calculate the eigenvalues for this matrix A square. You will get the eigenvalues as 4 and 1. So now my question is, Can you find any relation between eigenvalues of A and A square? You see, eigenvalues of A, 2 here, we get 4 here. Eigenvalue minus 1 here, we get 1 here. Is there any relation between these two? Yes, you are right. If I square this, you will get this number. If I square minus 1, we will get this plus 1. Am I right? So therefore, if lambda is an eigenvalue of A, then what are eigenvalues of lambda square? Yes, you are right. Lambda square. A square eigenvalues are lambda square. If lambda is an eigenvalue of A, then lambda square is the eigenvalue of A square. Am I right now? Next, you calculate what is A cube. You are going to get this one. A cube is minus 10, minus 18, 9 and 17. How do you calculate A cube? A cube is equal to A square into A. A square here we have, into A here we have. You multiply A square into A, you will get A cube. You calculate the eigenvalues for this. Finally, you are going to get 8 and minus 1 as the eigenvalues. Obviously, these are the cubes of eigenvalues of the matrix A. 2 cube is 8, minus 1 cube is minus 1. Similarly, we calculate A power 4. A power 4 is A square into A square. Multiply A square 2 times, you will get this one. And obviously, the eigenvalues of this are 16 and 1. 2 power 4 is 16, minus 1 power 4 is plus 1. What could be the eigenvalues of A power 5? Yes, you are right. Eigenvalues of A power 5 are 2 to the power 5. 2 to the power 5 is 32. Next, minus 1 to the power 5. Minus 1 to the power 5 is minus 1. Like that, we can find eigenvalue of matrix A to the any power. Got it? This is what is the property. What is the property? If lambda is the eigenvalue of the matrix A, then lambda square are the eigenvalues of the matrix A square. Lambda cube are the eigenvalues of the matrix A cube. In general, lambda power n are the eigenvalues of the matrix A to the power n. This is another important property. We shall see the proof in the next slide. Okay. The statement of this is like this. If lambda is an eigenvalue of A, then lambda square is an eigenvalue of A square. Lambda cube is an eigenvalue of A cube, and so on we can continue. In general, we can write lambda power n is the eigenvalue of A to the power n. Proof we shall see. As usual, you take let A be a square matrix and X be the eigenvector corresponding to the eigenvalue lambda. Similar proofs, 2 or 3 line proofs. You take A be a square matrix, X is the eigenvector corresponding to the eigenvalue lambda, and the familiar equation you write down. Then we have, what is the familiar equation? This is one. Ax is equal to lambda x. You should not remember this one. Ax is equal to lambda x. You remember? Whenever I write Ax is equal to lambda x, you should say like this: lambda is the eigenvalue of the matrix A, or X is the eigenvector of the matrix A corresponding to the eigenvalue lambda. You should say like this. Okay. What I do in the next step is pre-multiply the equation by A on both the sides. Multiply A both the sides. Pre-multiply, I am telling. So we get A into A of X is equal to A into lambda x. In the next step, what I do is I combine A and A, interchanging the brackets. A of X is equal to, I combine lambda with A, we get A lambda of X. Next, you know what is A into A? Obviously it is A square. X is equal to, I write A lambda as lambda into A. You remember, A into lambda can be written as lambda into A. This is possible only when lambda is a number. Remember, lambda is an eigenvalue. It is just a number. It is not a matrix. Suppose if lambda is a matrix, then you cannot suppose to write A lambda as lambda into A. Since lambda is a number, we can write like this. If lambda is not a number, if lambda is a matrix, then you cannot write A lambda as lambda into A. Since lambda is a number, we can write a lambda is equal to lambda into a of x. Just interchanging a and lambda. It is possible because lambda is a number. Next, what I do is, now again I combine a with x. LHS a square x as it is, lambda into, combine a with x, make the group of a and x like this. Next, in place of ax, can you tell me what we can write? Go to the first equation. What we have here, ax is equal to lambda x. So therefore, in place of ax, we can write lambda x. So therefore, we get a square x is equal to lambda of lambda x. Therefore, we get a square x is equal to, now combine lambda and lambda, make a group of that, we get lambda into lambda, that is lambda square x. Therefore, we have a square x is equal to lambda square x. Now compare this equation 1 with the first one, this equation. You see, in place of a, we are having a square here. In place of lambda, we are having lambda square here. If we have equation like this, we say lambda is the eigenvalue of matrix A. Similarly, if I have equation like this, we can conclude lambda square is the eigenvalue of the matrix A square. That is the proof of this one. Okay, we can continue this for some more powers of the matrix A. Other powers of the matrix A. How? Do one thing, that is lambda square is an eigenvalue of A square. What I do is, further we multiply A on either side of 1. A of A square x is equal to A of lambda square x. What we can prove like is A cube x is equal to lambda cube x. You multiply A on either side, you know, in the first equation. A of A square x is equal to A of lambda square x. A of A square we get, you know, A of A square is A cube. Okay, we get A cube here. Here A of lambda square. A of lambda square, interchange a lambda square and A, we get lambda square into Ax. Lambda square into, in place of Ax you write again lambda x. We get lambda square into lambda x, but lambda square into lambda is lambda cube. That's what we get. So therefore we get A cube x is equal to lambda cube x. Means we can conclude that lambda cube is the eigenvalue of A cube. So in general we can show that lambda power n is an eigenvalue of A to the power n. That is lambda cube is the eigenvalue of A cube and so on. In general what we can show? We can show that lambda power n is an eigenvalue of A to the power n. You see, it is very important. Why? Because if I have a matrix A, then you have asked to find eigenvalue of A to the power 50. You see how it is tedious if you calculate A to the power 50. Is it possible to calculate A power 50 so easily? A power 50 means multiply A 50 times, A into A into A into and so on 50 times, and then you have to calculate the eigenvalue of that. It is very tedious. Then how do you find the eigenvalues easily using this property? It is very easy. You just find out the eigenvalue of the matrix A. Then eigenvalue of A to the power 50 are nothing but the powers of the eigenvalues. You take the power eigenvalues of lambda, then the eigenvalues of A power 50 are nothing but lambda to the power 50. Take the power of eigenvalue to the power 50, you will get the eigenvalues. It is the important application of this property. Okay. Next. So now observe this table. We are having the same problem, matrix A 2 minus 1. I will find the inverse of this matrix. A inverse is equal to minus 5 by 2, minus 3, 3 by 2 and 2. You know how to find the inverse of a 2 cross 2 matrix. All of you know. I have written directly this one. For this matrix A inverse, I have determined in eigenvalues as 1 by 2 and minus 1. You calculate minus 5 by 2 lambda, minus 3, 3 by 2, 2 minus lambda, determinant is equal to 0. You calculate that one and evaluate. You are going to get the CH equation. And if you solve that CH equation, you are going to get these two values as the eigenvalues. Now observe the first and second rows. 2 is the eigenvalue. Here 1 by 2 is the eigenvalue for inverse. Minus 1 is the eigenvalue and minus 1 again is the eigenvalue for inverse. Is there any relation between eigenvalues of matrix and its inverse? Yes, it is a yes, there is a relation. 2 and eigenvalue of A inverse is 1 by 2. So therefore, if lambda is an eigenvalue of A, then 1 by lambda is the eigenvalue of A inverse. Is that right? What is in that is minus 1 by 1 is minus 1 only. You come here, I have taken a different matrix. B is equal to 2, 2, 2 minus 1. Eigenvalue of this matrix are 3 minus 2. If I find the inverse of this matrix B, we will get this one, 1 by 6, 1 by 3, 1 by 3 minus 1 by 3. And eigenvalue of the matrix B inverse are 1 by 3 and minus 1 by 2. Reciprocal of these eigenvalues. In general, what we can say is, if lambda is an eigenvalue, see, if lambda is an eigenvalue of the matrix, what we can say, if lambda is an eigenvalue of the matrix A, then 1 by lambda is the eigenvalue of the matrix A inverse. This is another important property. Okay, let us try to prove this in the next slide. You see, if lambda is an eigenvalue of non-singular matrix, A inverse must exist means that matrix must be non-singular. Determinant is not equal to 0. Then only inverse exists. You should remember this one. If lambda is an eigenvalue of non-singular matrix A, then you see number 1, 1 by lambda is an eigenvalue of A inverse. Lambda is an eigenvalue of A, then 1 by lambda is an eigenvalue of A inverse. This is first result. Second result is 1 by lambda into determinant of A is an eigenvalue of adjoint of the matrix A. Adjoint, you know how to find the adjoint in your PU classes. So 1 by lambda into determinant of A is an eigenvalue of adjoint of a matrix A. So we shall try to prove these two results one by one. These two results seems to be very lengthy, but they are not so lengthy. They are very easy. You see, if I prove the first one, it is very easy to prove the second one. You see, the proof of these properties, it is very simple. As usual, I am proving the first result, proof first one. As usual, you write A is the square matrix, X is the eigenvalue corresponding to the X is the eigenvector corresponding to the eigenvalue lambda. Then as usual, we have write down the equation Ax is equal to lambda x. You should remember, it is very important equation. You should remember this. Ax is equal to lambda x. And next, in order to prove the first result, what I do is I pre-multiply by A inverse on either side. Pre-multiply A inverse on either side of the equation. We get A inverse A is equal to A inverse Ax is equal to A inverse lambda x. Then next steps, interchange the bracket and use and all that, you are going to get the required answer. You see, next interchanging the bracket, A inverse Ax is equal to A in lambda. I am avoiding one step here. You write down this as A inverse into lambda and then invert that one, lambda into A inverse, interchange the bracket. I do all those. I am avoiding those two steps here and directly I write like this, lambda into A inverse x. A inverse into A, what is the value? A inverse into A, you remember, it is identity matrix. If I multiply A and its inverse, you are going to get the identity matrix. So we get I into X is equal to lambda into A inverse X. But what is I into X? It is X only. If I multiply any matrix with identity matrix, you are going to get the same matrix. So we get X is equal to lambda into A inverse X. What I do is, I bring lambda to LHS. So I get 1 by lambda into X. 1 by lambda into X is equal to A inverse X. I just invert this one. So LHS, RHS, I am interchanging. So we get A inverse X is equal to 1 by lambda X. This is the equation we are having. So now compare this equation with the first equation, this one. Compare this on the last equation. What do we have? If I have the equation like this, Ax is equal to lambda x, we say lambda is the eigenvalue of A. Similarly, if I have equation like this, what we can conclude is 1 by lambda is an eigenvalue of A inverse. That's all the proof. Only thing you should remember here is three things. First one is, remember this equation Ax is equal to lambda x. Next step is multiply, pre-multiply A inverse on either side. That is the important step you should remember. Do simplification, interchanging bracket and all that, you will arrive at this equation A inverse x is equal to 1 by lambda x. So compare this with the first equation. Therefore what we can say, 1 by lambda is the eigenvalues of A inverse. That's all the proof. This is the proof of the first one. Am I right? Now we have to prove the second result. 1 by lambda into determinant of A is an eigenvalue of adjoint of the matrix. Okay, it is very simple. In order to prove the second result, you remember we need to write every step here. We need to write every step here beginning from Ax is equal to lambda x. But I am continuing with this statement, last equation A inverse x is equal to 1 by lambda into x. I am continuing the proof with this sentence. Suppose if you ask the same question in examination, you are going to write the answer from beginning from Ax is equal to lambda x. You should remember this one. Let us try to prove the second result in the next slide. So we have this one. I'm saying again. You see, whenever I have asked to prove the second result, I have to first prove this result. A inverse x is equal to 1 by lambda into x. Okay, then only you continue with this. Next step is, you know, in your second PU classes there is a formula to find A inverse. Do you remember A inverse formula? Yeah, you are right. That is adjoint of A by determinant of A. Do you remember? The formula to find A inverse is adjoint of A by determinant of A. I am using that formula here. In place of A inverse, I am writing that formula adjoint of A by determinant of A into x is equal to 1 by lambda into x. In the next step, what I do is, I am transferring this determinant of A to RHS here. Okay, so in LHS we get adjoint of A into x is equal to the determinant of A comes here, and in RHS we get determinant of A by lambda into x. Okay, so observe this one. See, x here. So in place of lambda we are having determinant of A by lambda. In place of A we are having adjoint of A. So therefore what we can conclude is determinant of A by lambda or 1 by lambda into determinant of A is the eigenvalue of adjoint of A. That's all the proof. So determinant of A by lambda is the eigenvalue of the matrix adjoint of A. So these are all the some of the properties of eigenvalues and eigenvectors. So with this all the properties of eigenvalues and eigenvectors completed. Okay, thank you.